Hello everyone, I am Professor Shalini Sahay, Assistant Professor in EC Department, SIRT Bhopal. Today in this lecture, we are going to discuss about the microwave components and the matching techniques. The operation of an antenna system over a frequency range is not completely dependent upon the frequency response of the antenna element itself, but rather on the frequency characteristics of the transmission line and antenna element combination. In practice, the characteristic impedance of the transmission line is usually real, whereas that of the antenna element is complex. So the main importance of this transmission line with antenna element is that the impedance matching is must. So transmission line impedance is real and we have to match with the impedance of the antenna, which is in complex in nature. Also, there will be the variation of the frequency between these two elements. Thus, efficient coupling matching network must be designed which attempts to match the characteristics of the two devices over the desired frequency range. So matching technique is must, as we have to match the different load nature of the elements and with the different frequencies of these two elements. For this, now we'll discuss the first matching technique, that is known as the stub matching. Ideal matching at a given frequency can be accomplished by placing a short or open circuited shunt a distance s from the transmission line antenna element connection. So a transmission line whose length is L is connected in shunt with the regular transmission line. So this shunt connection of transmission line at a particular distance, which is known as the stub, assuming that a real characteristic impedance, the length is controlled so to make the real part of the antenna element impedance equal to the characteristic impedance of the transmission line. So if we want to match the antenna with the transmission line, so we have to match the load. For this load matching, we will connect a shunt line whose points represent the matching of the impedances of the antenna with the transmission line. The length L of the shunt line is varied until the succipitance of the stub is equal in magnitude but opposite in phase to the line input succipitance at the point of transmission line, that is the shunt element connection. So this succipitance of the stub should be equal to the magnitude, but it is opposite in phase. Now the short circuit stub is more practical because an equivalent short can be created by a pin connection in a coaxial cable in a waveguide. This preserves the overall length of the stub line for matching, which may require longer length stubs. A single stub with a variable length cannot always match with the antenna's load impedances. So a double stub matching arrangement is positioned a fixed distance from the load with the length of each stub variable and separated by a constant length L will match a greater range of antenna impedances. So sometimes a single stub does not work. So we have to make a multiple connection of the stub at different points on the transmission line so as to match the impedances between the transmission line and the antenna. Sometimes one stub is fixed and the second one is changed, or it is an variable whose position can be changed with respect to the first one. The length of the L of the shunt is varied until the succipitance of the stub is equal in magnitude but opposite in phase. So sometimes it is always kept varying, or as per the requirement, sometimes we'll require double or triple stub matchings. Now these are the quarter wavelength transform which can be designed So if the length of the transmission line is considered to be as lambda by 4, so it's known as the quarter wavelength transformer, and it is defined on the variable section like single section, multiple sections, binomial designs, Chebyshev design. Now, if we see the single section design, another techniques that can be used to match the antenna to the transmission line is to use a lambda by 4 transformer. If the impedance of the antenna is real, then the transformer is attached directly to the load. So here we have used as the transmission line as a transformer by keeping its length lambda by 4. So if the impedance of the antenna is kept real, then transformer is attached directly to the load. However, if the antenna impedance is complex, then the transformer is placed at a distance away from the antenna. So this is the distance which we have to keep the antenna impedance, antenna kept at a distance away. So the transformer is placed at a distance S0 away from the antenna. And this distance S0 is so chosen that the input impedance towards the load, it is real and it is designated as Rin. So the main purpose is first to make the impedance in real term. To provide a match, the transformer characteristics impedance Z1 should be, it is the product under root square of Rin into Z0, where Z0 is the characteristic impedance which is kept as real of the input transmission line. The transformer is usually another transmission line and with the desired characteristic impedance. Now, because the characteristic impedance of most of the transmission lines are limited in range and values, so the quarter wave line length transformer technique is most suitable when used with microstrip transmission line. In microstrip, what we take the characteristic impedance is generally changed by simply varying the width of the center conductor. Now, if we take the multiple sections where the matching that are less sensitive to frequency variations and that provide broader bandwidth, which require multiple section of single sections. So in multiple section, we take number of single section with the length of lambda by 4. In fact, the number and the characteristic impedance of each section can be designed so that the reflection coefficient follows within the desired frequency bandwidth. Prescribed variations which are symmetrical about the center frequency. So if we take the number of simple sections, then what we have to consider is that the reflection coefficient should follow within the bandwidth. So all things should be done within the desired frequency bandwidth. The antenna load impedance will again be assumed to be real. If it is not, then antenna element must be connected to the transformer at a point S0 along the transmission line and where the input impedance is real. In general, the multiple section, either binomial or Chebyshev, provides greater bandwidths than a single section. As the number of sections increases, the bandwidth also increases. Now, if we take the number of sections, then the bandwidth is also increased. Now, the advantage of the binomial design is that the reflection coefficient values within the bandwidth monotonically decreases from both ends towards the center, and thus the values are always smaller than acceptable design value. So if the main advantage of his binomial design is that the bandwidth is coincide through the center, and thus the values are always smaller than an acceptable and designed value. Now for the Chebyshev design, the reflection coefficient values within the design bandwidth are equal or smaller than the acceptable and design values. So these are the consideration which we must consider while connecting the single section, multiple section, either binomial or Chebyshev. So the main point is that the reflection coefficient should be taken in the desirable bandwidth. The number of times the reflection coefficient reaches the maximum ripple value within the bandwidth is determined by the number of sections. In fact, for an even number of sections, the reflection coefficient at the design center frequency is equal to its maximum allowable value, while for an odd number of the section, it is 0. So even when we take the number of section even, then we take the value of the desired center frequency to the maximum value. If we take the number of sections in odd term, then it is considered as 0. For a maximum tolerable reflection coefficient, the N-section Chebyshev transformer provides a larger bandwidth than a corresponding N-section design. For a given bandwidth, the maximum tolerable reflection coefficient is smaller for Chebyshev design. So these are the different matching techniques which we have to consider the different ranges of the center frequency. We have to consider the different tolerable reflection coefficient so that the section can transfer the information for a larger bandwidth and for the acceptable bandwidth. Thank you.